Hello everyone. We are going to go over chapter 9, which is a chapter that discusses the topic of solutions. A solution, as you can see in the first bullet point, is defined as a homogeneous mixture of two or more substances. Now, these two substances, we are going to give them a specific name. In this case, as you can see, we have the components named solutes, which is going to be the substance that we have present in lesser amount, and we have a solvent, which we have present in a greater amount. Understand that when we are making a solution, we are always, solutions are made of one solvent and one or more solutes. Understand that in order for a solution or this homogeneous mixture to be made, the interactions between the solvent and the solute have to be stronger than the solvent to itself and the solute to itself. Now, solutions come in all three states of matter. As you can see in table 9.1, solutions can be in gas form, in liquid form, and in solid form. What determines if you have a particular homogeneous mixture or solution in one of the three states of matter that we have described is the solvent. So this is what determines the state of matter for a given solution. Now let's look at some examples. So as you can see in table 9.1, we have an example of a gas solution. And on the right side of the slide, we have a pie chart that it illustrates the different components of air. So as you can see in table 9.1, the solvent, specifically in air, is going to be nitrogen. And in the pie chart, you can see that 78% of the air that is around us is made out of nitrogen. Now, even though in table 9.1 it says that the solute is oxygen, that is because that's the primary solute present in air. But there's other components in air. For example, there's argon, the CO2, and even water vapor. Now, let's move to a second example. When it comes to liquid solutions, as you can see, the solutes can be in all three states of matter. We can have solutes that are gas, we can have solutes that are liquid, we can have solutes that are solid, but again, our solvent is always going to be liquid. And specifically, we have the example of vinegar. And in this case, our solvent is going to be water, and our primary solute is going to be acetic acid. The last type of solution, which is one that sometimes we don't think of it often, is going to be a solid solution. And remember that when it comes to solid solutions, these are going to be, again, a solid solvent and a solid solute. Now, here we have elements that are going to be just combined but not physically or chemically linked. So for the solid solutions, all of these are examples of alloys. And hopefully you remember from chapter 3 that an alloy, again, is elements that are physically combined but that are not chemically linked. And many instruments are made out of brass. And as you can see, brass comes from the combination of zinc as a solute and copper as a solvent. Now, one of the most important solvents that we need to be familiar with is water. As you can see, is the most common solvent in nature. We learned already in chapter 6 how water is a polar molecule because it's a tetrahedral molecule that does not have 4 identical bonds. So substances are going to interact with water in a very particular way. As we go into biochemistry, we are going to see how water is interacting with biomolecules and gives rise to many important structures in our body. Now, because water is the most common solvent, we should know how things interact with water, or in general, how things interact with solvents. So now we have to define what is the rule of thumb when it comes to making solutions, which that is that like dissolves like. So this rule of thumb basically says that polar solvents interact with polar solutes and non-polar solvents interact with non-polar solutes. That's the general rule. So as you can see in the first bullet point, it says that ions are attracted to polar solvents. And the reason why that is that remember that ions are going to have a metal that is designed as I assign a capital M, and that is going to be a cation. And we're going to have a non-metal that, as you can see, I place it as a NM, and that's going to be an anion. Whenever we have a polar solvent, remember that we're going to have the delta negative and the delta positive sign because of the polarity in the molecule. So when we have ions interacting with polar solvents, understand that what happens is that the cation will be interacting with the partial negative, while the anion is going to be interacting with the partial positive of your polar solvent. Now, as I described, in like dissolves like, polar molecules are attracted to polar solvents. Non-polar molecules are attracted to non-polar solvents. And understand that there's going to be times where we have a molecule that has both features. So for example, when we're talking about fatty acids, and this is something that we're going to talk about later in the semester, these molecules, I'm just going to illustrate an example of a fatty acid. Okay, here I'm going to now write in the carbons and the hydrogens. So in this fatty acid, as you can see, we have a polar side. Understand that these are carbons and hydrogens in the right side of the molecule. So in this molecule, we're going to have a polar side, which is highlighted in green. And we're going to have a non-polar side, which is highlighted in orange. So understand that in molecules where we have both polar and non-polar components, by definition, when they are interacting with a particular solvent, understand that it depends on the length of that non-polar character. So for example, in this one, even though there is a polar character, overall, the molecule is non-polar because, as you can see, there's a larger component of the non-polar character. So that means that a molecule like this will be able to combine with a non-polar solvent. This explains why oil and water do not mix, because oils have molecules like these fatty acids. Now, It is very important that you guys are able to determine if a particular ionic compound is soluble in water, because not all of them are available, are able to dissolve in water. So for that, in order to determine if something is soluble in water, you need to utilize table 9.8, which that gives you what we called in chemistry solubility rules, okay? And I'm going to illustrate how to utilize table 9.8 to solve problems that we have in the worksheet. So as you can see, if you printed the worksheet, right now I'm going to do problem B in the worksheet. As you can see, the instruction says, predict the products of the following reactions and use solubility rules to determine which of the products will precipitate. Precipitate means that it will form a solid. So here, if these compounds are able to dissolve in water, we are going to design them as aqueous. So we're going to put an AQ in parentheses just to designate that they are aqueous solutions. So let's get started. The first set of reactions that we have, all of these are double replacement reactions. And remember that in double replacement reactions, what we have is the exchange of partners in the reactants, and that's how we're going to form products. So let's go over the first two compounds. Here we have silver nitrate, and the chemical formula for silver nitrate is going to be AgNO3. We also have potassium phosphate. Potassium phosphate, the chemical formula is K3PO4. So to illustrate how both of these compounds are soluble in water, I'm going to look at table 9.8. So as you can see, the way that we use table 9.8 is first identify the anion. So for example, in silver nitrate, our anion is going to be nitrate. Nitrate, as you can see, is always soluble in water. Now, because you can see that there is nothing that can be paired with nitrate in order to make it insoluble, that's why you see none. That means that nitrate is an aqueous solution. Let's move on to the next one. We have phosphate. Now, as you can see, in this table, it says that an ionic solid is insoluble if it contains phosphate. But there's something special about phosphate. Understand that is phosphate, hydroxide, carbonate, or sulfide are paired with any of these four: lithium, sodium, potassium, or ammonium. They become soluble. So in the example that we have potassium phosphate. So that means that potassium phosphate is an aqueous solution because we have phosphate paired with potassium. Now, let's now predict the product of the reaction. And when we have the exchange of ions, remember that now silver is going to be with phosphate. So the product of this reaction is going to be Ag3PO4. Ag3, let me rewrite it. It's going to be Ag3PO4. And then the other compound is going to be KNO3. Remember, in a double replacement reaction, the general structure, which I'm going to write in the bottom. If you have compound A and B and compound C and D, you're going to assume that A is the cation, B is the anion, C is a cation, D is an anion. So when they exchange, we're going to have now pairs that are A and D, C and B. That's how we predict the product. Now let's determine if this silver phosphate and this potassium nitrate are either aqueous or solid. So your options for predicting the products is always going to be, for these type of problems, aqueous or solid. So let's get started with silver phosphate. So when it comes to silver phosphate, first we look at the anion, which is phosphate. And as you can see, a solid that contains phosphate is always insoluble. But notice that in this time, that phosphate is going to be with silver because the cation and the anion are both on the insoluble section. Then that means that silver phosphate is going to be solid. When it comes to potassium nitrate, ionic solids that contain nitrate are always soluble. And as you can see, there's no exceptions. So nothing that is paired with nitrate can be insoluble. So that means that in this case, potassium nitrate is aqueous. Now, the rest of the answers for the worksheet, I'm going to be posting on Canvas. So understand that you can verify all the problems that you're doing on Canvas. Now, another way in which I can ask questions about if something is soluble or not is, again, utilizing table 9.8 to determine if it's an ionic compound. So again, this table is only for ionic solids. Let me make that clear. Use for ionic compounds. Okay. Now, as you can see in part C of the worksheet, we have a list of compounds. Some are ionic, but other ones are covalent. So I'm just going to illustrate what will be the difference when we are trying to determine if I'm given a combination of ionic compounds and covalent compounds. How do I determine what type of solvent they are able to combine with to make a homogeneous mixture? So as you can see here, in part C, you're trying to determine the solvent, and your options of solvents are going to be water as your polar solvent, and we have hexane as your non-polar solvent. So to illustrate how to deal with these problems, I'm going to specifically do number 1, number 3, number 13, and number 16. Okay, so number 1 and number 3 are going to be specifically covalent compounds. Number 13 and number 16 are going to be ionic. So we already learned previously how we deal with ionics. Okay, now whenever we have an ionic compound, remember that we are going to direct our attention to table 9.8. So the first thing that you should know is how to write a specific chemical formula. So for silver hydroxide, okay, you should know that silver hydroxide is going to be AgOH. Okay, sodium nitrate is going to be NaNO3. Why do we need to do that? Because as you can see in table 9.8, we only have chemical formulas. We don't have names. So let's determine what will be the most appropriate solvent for these, okay? So on number 13, we have, as you can see, hydroxide, which is any compound that contains it is going to be insoluble. And that hydroxide is paired with silver. So based on solubility rules, you know that water is not going to be an appropriate solvent for it. So in this case, you will predict that we need hexane as its solvent because this compound is not soluble in water. So it's going to be able to dissolve in a non-polar solvent. Let's deal with the next one. So for number 16, as you can see, we have nitrate, okay? And nitrate is paired with sodium. So as you can see, if a solid contains these pairs, okay, that means that it's going to be soluble in water. So because sodium nitrate is soluble in water, then we are going to select water as its solvent. Again, when you have ionic compounds, you have to utilize table 9.8. Let's move on to cases in which we have covalent compounds. So with covalent compounds, we have to go back to drawing Lewis structures. So at this time, I'm going to write the Lewis structure for CH3Cl, and I'm going to write the Lewis structure for C2H2. Now, when you have a covalent compound, the first step is to write the Lewis structure. Then after that, you have to utilize the rules that we learned about polarity to determine if your molecule overall is polar or if the molecule is nonpolar. If we look at CH3Cl, this is a tetrahedral molecule that does not have 4 identical groups. So that means that this molecule is polar. If we look at the Lewis structures of C2H2, this molecule has symmetry. And if we fold it, the left looks like the right. So since this linear molecule has identical groups on either side, this molecule is nonpolar. Previously, I showed you guys how if you have a polar molecule, then they're going to be dissolved and they can be able to combine with polar solvents. So in this case, because my first molecule is polar, that means that the solvent that is going to be utilized to make a solution is going to be water. Because remember, the molecule is polar, so it needs a polar solvent, that in this case is water. Now, if we look at the molecule C2H2, because the molecule is nonpolar, then it needs a nonpolar solvent, like hexane, in order to make a solution. So the answer for number 3 is hexane. Okay? So as I mentioned before, the rest of the answers for the worksheet are going to be posted in a separate file for this worksheet. Okay, so it's going to be posted on Canvas. So the last topic that I want to discuss in this lecture is going to be attractive forces and how that affects solubility. So we already learned that polar molecules dissolve in polar solvents. So understand that the reason why this happens is because we have a series of attractive forces that are going to happen. So those include, for polar molecules and polar solvents, ion dipole, hydrogen bond, and dipole-dipole. Remember that in the ion dipole, as I mentioned previously, the cation like we have in this example, a cation is going to be interacting with the delta negative, okay? So these molecules that you guys see here, this is water. And I'm just going to illustrate it here. So these are water molecules in which these are going to be the hydrogens. That's hydrogen. And this is oxygen. And remember that when we have the partial charges, oxygen is delta minus, hydrogen is delta plus. So if we have a cation, it's going to be interacting with the delta negative in the water. Remember that hydrogen bonding is also a type of interaction where we have a hyperdipole-dipole. And then lastly, we have dipole-dipole attractions. Again, this is when we have the pairing of the delta positive of a molecule interacts with the delta minus of another molecule. The delta minus of the molecule interacts with the delta plus of the molecule, okay? So those opposite charges on either molecule are going to be interacting with one another. So when it comes to nonpolar molecules interacting with nonpolar molecules, understand that this happens because of weak attractive forces. And as we learned previously, the weakest attractive force that is present is going to be dispersion forces. So when we have nonpolar molecules reacting with nonpolar solvents, the attractive force that makes them interact is going to be dispersion forces. Now, if a molecule has both polar and nonpolar components to it, remember that it depends on the overall polarity of the molecule to see what's going to be the solvent that I can interact with. So in general terms, we know that oil and water don't mix. So this implies that oil does not like polar solvents. So if we look at the molecule, for example, here we have olive oil. If we look at what olive oil is made out of, which is oleic acid, and that's the structure that we see, this molecule, even though it has a polar component, and similar to how I labeled it before, the polar component is what I highlighted in green. The nonpolar component is what I highlighted in orange, because it contains a large nonpolar portion overall. The molecule is nonpolar. So that being said, in cases like this, and as we progress this semester, we are going to be observing that, for example, oils are going to be soluble in this case. And for example, a nonpolar solvent like hexane. In the next lecture, we are going to be covering section 9.2 and 9.3.